Welcome to The Explainer. Today, we're unpacking the incredibly dense, absolutely fascinating mathematics of the Adelic Langlands Program. If you've ever wondered how the chaotic quantum world scales up without breaking down, and the exact equations we might use to one day build perfectly stable quantum computers, you are definitely in the right place. Let's get right into the math. We're looking at a true mathematical translation of reality here. We're going to map exactly how chaotic, microscopic quantum states are shepherded through complex, nonlinear equations to achieve this beautiful global arithmetic stability. It's a wild journey from local quantum static all the way up to global geometric harmony. Here's our roadmap for the explainer. First, the Adelic quantum lift, then the Lindblad master equation, followed by thermodynamics and nonlinear transport, entanglement in linked networks, geometry and topological protection, and finally, the ultimate stable synthesis. Starting right off with part 1, the Adelic quantum lift. Before we throw the heavy equations up on the board, let's set our baseline. We're completely leaving behind the classical flat space you might be used to, isolated fermion modes and simple scalar phase shifts. Instead, we're jumping into the Adelic Langlands space. We're trading simple points for localized Adelic wave functions and massive anomalous Hecky block matrices. Think of it like upgrading from a simple, flat 2D map to a deeply complex, knotted, multidimensional topography. This perfectly illustrates that structural lift. Just look at how the defect projection operator down at the bottom transforms. What was once a simple closed system counting statistic mathematically morphs into a horizontally stable, three-dimensional, knotted boundary divisor current. Yeah, I know it's a mouthful, but visually, it just means the state isn't just sitting there anymore. It's being stretched across the entire adele ring. Okay, let's look at the specific mathematical mutation happening in the equations here. Notice the transition from left to right. That simple point-like U1 scalar shift literally mutates into a massive non-abelian block matrix. We're replacing scalar factors with quantized phase steps, and the internal matrix ranks are dynamically scaling to match the simple fusion objects in the category. Pulling a key variable from that equation, we have the colored Jones polynomial. And this isn't just some abstract number. It turns out actual knot geometry acts as mathematical armor. This polynomial physically embeds that knot geometry directly into our phase rotation matrix. It acts as a shield, mathematically protecting the state's structural integrity as it prepares to move. So our newly armored quantum state is starting its journey through this Adelic space, but that brings up a massive question. What mathematical engine is actually driving its decoherence? How do these equations filter out the noise over time? Which brings us to part 2, the Lindblad master equation. All right, let's break down this explicit time evolution equation, reading it from left to right. In that first bracket, you see the open quantum system evolving via a unitary Hamiltonian. Standard stuff, right? But it doesn't stop there. It's immediately subjected to those non-invertible jump operators in the middle, which stochastically scatter amplitudes across Riemann sheets. Finally, the anti-commutator on the far right acts as the ultimate mathematical friction. It completely collapses the dissipative channels into an integrated stress-energy potential, acting as a rigorous topological filter. If we look at the physical implications of this math, it acts like a cuspidality pump. Basically, it's a mathematical centrifuge. It systematically spins away the chaotic, high-frequency noise by forcing the off-diagonal coherence channels to decay exponentially fast. It strips away those chaotic fluctuations, forcing our traveling state to settle securely onto stable, isolated outlier representation rails. But wait, there's a huge threat looming on this journey. In an unregularized quantum system, what happens when our classical determinant hits a critical node and tries to drop to absolute zero? Normally, this signals a catastrophic wave function collapse. And that is exactly where part 3 comes in, thermodynamics and nonlinear transport. Check out this massive spike right in the center of the graph. That's our BBB crossover front. That spike is literally a topological surge. The math here is measuring the exact thermodynamic information dump required to regularize the wave function's collapse. The system sheds its continuous bulk data into the modular environment right before the stretched exponential shield dramatically crushes the entropy back to zero, miraculously settling the whole system into a stable vacuum. So instead of just shattering at that critical node, the state relies on the nonlinear transport equations shown here. Specifically, look at the Hastings-McLeod solution of the Painlevé II equation. It takes that chaotic, highly oscillatory multi-channel mixing on the left, runs it through the differential equation, and snaps it cleanly into the stable, exponentially decaying profile you see on the right. In the math world, we call this process an isomonodromic smoothing filter, which is really just a terrifyingly complex way of saying it's a mathematical shock absorber. It continuously bends the linear state space so the classical trajectories are caught safely. It transforms a dangerous, sharp classical zero into a fuzzy, highly protected quantum interface layer. Let's complicate things a bit in part 4, entanglement in linked networks. Take a really close look at the linked dissipation matrix on the right here. When Hopf loops are physically linked together, the Gauss linking number kicks in. And because those physical loops are locked, the math literally forces a permanent zero right into the bottom left element of that matrix. This is huge because it creates a chiral, strictly asymmetric flow. The transport equations can no longer be decoupled smoothly. We call this the topological diode principle. Think of it as a one-way street for quantum information. Our geodesic paths glide without resistance in one direction, but they are aggressively stripped of their non-tempered kinetic energy in the other. It acts as a directional geometric pump, forcing an asynchronous dumping of phase information that irreversibly stabilizes our wave function. Now for the ultimate destination, Part 5, Geometry and Topological Protection. All right, brace yourselves for this one. This massive formula on screen is the Arakelov analytic torsion tensor. And it isn't just there to torture grad students. It proves that our state spectral partitions are physically warped by the non-invertible category twists of the defect loop. It perfectly balances the baseline untwisted torsion, the non-abelian S-matrix transport, and those conical deficit parameters bound by the colored Jones polynomial we talked about earlier. It literally locks the global geometry in place. And here's where the mathematical magic really happens. When we equate that exact torsion tensor to this fractional supersymmetric index formula, we get an absolute ultraviolet regularizer. Because this index is driven by colored Jones polynomials, it evaluates to a highly specific fractional field element. Landing on a fraction instead of a whole number means it completely avoids those deadly zero nodes we were sweating about earlier. It fully shields our mathematical manifold from geometric collapse. Which brings us to our final takeaway, Part 6, the ultimate stable synthesis. Let's bring all these incredible mathematical rules together. We start at the origin with the microscopic quantum lift, move through the Painlevé II transport interfaces, get filtered by the Adelic Lindblad master equation, and finally arrive at global topological protection. We can literally see how these equations physically weave an uncollapseable semi-classical shadow directly out of quantum chaos. The symmetries prevent the universe's math from breaking down at the nodes. It leaves us with a pretty profound question. If this invisible mathematical architecture flawlessly self-corrects like this, what other new structural mysteries are hidden in the Adele ring, waiting to be calculated? Thanks for joining me on this explainer. I really hope this helped illuminate the math behind the framework for you.